All right, hey everybody. This is Mr. O'Connell visiting. Hey, this is some short notes for chapter 23, part 3, the last part of chapter 23. That's hypothesis testing for means. This is a one sample t-test. Since this isn't a live meet between me and you, I will hold a live meeting either tomorrow or the day after to take questions, go over this, but this is just to start you guys off. So, uh, the good thing about this, assumptions and conditions are the same as the t interval that we did last week. So you can remember that uh, independent and random condition is still there, that if they're randomly selected, it's going to be the samples are independent of each other. You still have a 10% rule and the nearly normal condition. I'll fix that really quick. That's a nearly normal condition. The n got left behind there. These are all the same. You should be able to get those from notes last week if you don't remember. Also, good news, this hypothesis test is for means, but you've already done hypothesis testing for proportions and percents. The procedure is basically the same. So that procedure, remind yourself, you're going to start off with the assumptions and conditions, A and C. Then you're going to write your hypotheses, null and alternate. Then find the p-value with a CDF. Usually that would have been your calculator, but I'm going to show you how to do that with a website, Desmos. But that is your p-value you're finding. And then you decide if you reject or if you don't reject, fail to reject. The one difference here that you're going to be experiencing is that you have t-scores instead of z-scores. T-scores being the sample mean x bar minus the population mean that you're getting from your null hypothesis over the standard error of your sample means. Uh, if you don't remember what the standard error of sample means, that's the standard deviation of your population over the square root of your sample size n right here. This is going to give you your t-score. And like I just said a couple seconds ago, use Desmos for your TCDF. Okay, I'll show you that. Null hypothesis and alternate hypothesis, instead of using p equals, this is going to be mu, the population mean, the mean of all of the population, not just your sample. It's going to be equal to in your null. And in your alternate, it's either greater than, less than, or not equal to. Remember that not equal to, you're going to be doubling your p-value because you're testing both sides of the t-curve. Just as another reminder, have this handy, that you're rejecting your null. If your p-value is less than alpha, the problem might state alpha, but if it doesn't, just go with 0.05. 5% is pretty standard. So you reject your null if your p-value is less than alpha. That means that your evidence is significant. The evidence being your x bar, that is significant. We don't think that that was just by chance. And then scale this up. You're going to fail to reject if your p-value is not less than alpha. That means your evidence, your x bar, was not significant. Okay, so let me give you a little example here. So, a coffee machine dispenses coffee into paper cups. You're supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. Here are the amounts measured in a random sample, random keyword, of 20 cups. Is there evidence, or is there significant evidence, that the machine is shortchanging customers? Just for starters, kind of look at this. Under, 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 under. That is a lot of under pores. So you might think that, just predicting that they are going to be, that the mean might be less. I did some math in advance. I know usually on a calculator you put it in a list and it'd give you a bunch of statistics, and you don't have that now, so I'm giving it to you. So the sample right here, the mean of all of those is 9.85. On average, a coffee, when they're supposed to be getting 10 ounces, is getting 9.85. And the standard deviation right here is 0.1986. Okay, let's start with our hypotheses. Now, by the way, you will not have to do any of this by hand on this year's AP since they've gone out on a limb saying all calculations are going to be able to be done with pencil only. Okay, so it says random, so cups are randomly selected. And if you hear a toddler in the background, that is definitely my son, Liam. Cups are randomly selected. The 20 cups are less than 10% of all coffees served. He's behind the chair in here. Let's see if there's a way to pause this. I'm not seeing it. So, okay. Now, in the past, you'd have to prove that this is a nearly normal condition. But I'll tell you that with the restrictions on this year's AP, you can just say, I'm assuming it comes from a nearly normal population. And actually, with a sample size of 20, it just needs to make sure it's not severely skewed. So sample size 20 is actually decent. So as long as it's like kind of unimodal and symmetric and the skew isn't severe, that should be good enough. So you can move on, proceed with a one sample t-test. Remember, it's the world of t-test, t-intervals, because these are means. Move on to our hypotheses. Null, alternate. So remember, a null is about what is originally believed to be true. So it's advertised you're supposed to get 10 ounces. So I'm saying the null hypothesis, 10 ounces. This person, I didn't mean to write that. This person is claiming that they're being underpoured. So this is going to be that the alternate that the population average you are being served less than 10 ounces. Okay, so this is only going to be a one tail. All right, so we have our T curve. There are, remember, degrees of freedom is n minus 1 here. Since it's one sample, 20 minus 1, I want 19 degrees of freedom. Let's come up with our standard, let's get our T. So remember that's x bar minus mu over our population standard deviation over square root of n. So that is going up, 985 minus the 10 over, we have our standard deviation of 0.1986 over square root of 20, and I got negative 3.37. You can do a little prediction because our sample 985 is less than our null, so this should be negative. Okay? All right. So our T distribution with 19 degrees of freedom, no context, just going up and down by the standard errors. So we are getting from our sample negative 3.3. We are way far in this tail. All right, so this is, I'm expecting this to be low, but I have to take it to Desmos in order to do that. And I left my keyboard in the other room, so hum along with me for just a second. Zoe, say hi. And Zoe, say bye. Hey, Zoe. Hey, go play with Mommy for a second, okay? Please? All right, well, she's just my helper now. So go to Desmos.com. And you're going to graph.
The photograph.
Yeah, she says it. What are you eating?
Egg.
Yeah, this is on Easter, so she's eating an Easter egg. So click this little thing that I did in the bottom left. Go to Functions. Go to Distributions. T-Distributions. And it'll go up there. First thing it asks for is degrees of freedom, which was 19. So we had a sample size 20. What is that?
I don't.
You said you don't know? All right, so you want the TCDF function here. And going back to where we were, we want this little corner right here. So it really goes to negative infinity. We'll keep the negative infinity as the minimum up to negative 3.31. And it's given us 0.0018.
You do that.
And that's our p-value. So we don't double it because it's just a one tail, but that's a way low probability. 0.18 of 1%. So you could say with such a low p-value, we're rejecting. Reject null hypothesis.
Yeah.
And she is spitting this egg out all over the floor, but I'm going to finish this up. Reject the null hypothesis.
See.
Yeah, that's a yolk.
It's a big one. There's a yolk.
Reject the null hypothesis. There is significant evidence that the population mean of coffee pours is less than 10 ounce.
And you share?
You want to sign this really quick?
Yeah. And you
All right. Well, everybody else, me and Zoe are going to go now. Zoe's about bedtime, right? All right. Well, anyways, have a good one. I'm going to go live probably Tuesday. Contact me if you have questions. Have a good one.